Welcome to the stopping distance higher questions for the trilogy and the triple students. So the first question, the stopping distance of a vehicle is made up of two parts, the thinking distance and the braking distance. What is meant by thinking distance? So thinking distance is the distance the vehicle travels during the reaction time of the driver, or it's the distance the vehicle travels whilst the driver reacts. State two factors that affect thinking distance. So here I've listed 5, but any 2 would have done for the 2 marks. So tiredness, alcohol, drugs, speed and age will all affect the thinking distance, so will all affect the driver's ability to react. Pause the screen as these answers are about to be removed. So question 1 part B. Figure 1 shows a distance time graph for a car travelling at 15 meters per second. So on the y-axis we've got distance, on the x-axis we've got time. At the end of the race, the car is travelling at 5.2 meters per second. The brakes are applied, causing the car to slow down and stop. The brakes apply a constant force of 855 newtons in the opposite direction to the car's motion. The mass of the car is 950 kilograms. Calculate the braking distance travelled by the car. Okay, you've been given a lot of information in this question, so I recommend bugging the question, boxing command words and underlining anything we think is important. So I've underlined all the important parts of the question, and I've actually given you the equation that you need to use, because it's a calculate question. You know we're going to need to use an equation. In your exams, you would have to identify this equation from the list of equations you get in the physics equation sheet. However, because I didn't attach a sheet, I thought I'd give you the equation. So how could you know that you need to use this equation? The clue is it's a constant force. Okay, if it has a constant force, that also means it's going to be a constant acceleration, or in this case it's deacceleration, because the car is slowing down to a stop. And this equation here applies for uniform, which is the same as constant acceleration. So that constant force was the clue that we should use this equation here at some point. We're not given acceleration in the question. Okay, if we have a look, it's a 6-mark question, which is quite a lot of marks, which actually tells us if we don't have acceleration, we're going to have to find it, and we're going to have to find it by using another equation. What we are given is the force and the mass, and so we can use Newton's second law, F equals ma, or force equals mass times acceleration, to find the acceleration. So that's going to be step 1. First, rearrange the equation to find acceleration and find acceleration. So A is equal to the force divided by the mass. Therefore, the force is 855 newtons and the mass is 950 kilograms. So we get an answer of 0.9 meters per second squared. But looking back at the question, because it causes the car to slow down and the force is applied in the opposite direction to the car's motion, that means we know that the acceleration, or it is in fact deceleration, so therefore it has to be negative. So our value for acceleration is minus 0.9 meters per second squared. Next part of the question, we want to find the braking distance. Looking at this equation, it doesn't have braking distance in it, but it does have distance. So we need to rearrange this equation. The first thing we need to do to have distance, the subject. Okay, so have a look at the word equation and then look at the equation underneath. The final velocity is represented by the letter V. The initial, or the start velocity, is represented by the letter U. 2 is represented by the number 2, and acceleration, the letter A, and distance, we use the letter S. So we need to rearrange it to make S the subject. So rearranging that, we have the final velocity squared minus the initial velocity squared, all in brackets, divided by 2 times the acceleration is equal to the distance. So now, what we need to do is go back to the information we've underlined and try and link that to these symbols. So 5.2 meters per second, that's the speed of the car traveling at the end of the race. But as the brakes are applied, it slows down to a stop. So this 5.2 is actually the starting velocity of our car. But the car comes down to a stop after the brakes are applied. So that means the final velocity is 0 because it has stopped. So now we've got all the variables we need to calculate the distance. So A is minus 0.9, V is 0, and U is 5.2. So plugging those into equation, making sure that we get the brackets correctly around the V minus U squared, and then see what answer we get given. So when you plug that in the calculator, you get an answer of 15.022 recurring, but you can round that down to 15.0, and there's 3 significant figures, which is the highest amount of significant figures used in the question, so we just match that. Please pause the video as all the answers will disappear as I move on to the next question. So question 2. Figure 2 shows a velocity time graph for a short car journey. Looking at figure 2, we've got the velocity on the y-axis, and we've got time on the x-axis. First question asks us to determine the acceleration of the car in the first 20 seconds of the journey. Give the unit. So, first thing I've done is boxed determine. We've been given a graph and we are asked to determine the acceleration, so we've got to use the data from the graph to calculate the acceleration. So there is an equation for acceleration which says the change in velocity divided by the change in time gives us the acceleration. Therefore, acceleration is the rate of change of velocity. So we're given 20 seconds, or we're asked to calculate the acceleration in the first 20 seconds. And so that's only going to be up to this point here on the graph. What is the change of velocity in that time? It changes, so it starts at 0 and it ends at 12 at this point. So the change in velocity is going to be 12 meters per second. And the change in time is 20 seconds. And so putting that in the equation, 12 divided by 20 gives us 0.6. And the units is meters per second squared. See, velocity is meters per second. If we divide by another second, we get squared for the seconds. Okay. Part B says determine the total distance travelled by the car during the journey shown in figure 2. Again, this question is asked us to determine, so we're going to have to use the data from the graph to find out the total distance travelled by the car. So we have a velocity time graph, and whenever we have a velocity time graph, the area under the velocity time graph will give us the distance. And this is a really crucial thing to spot, okay? So distance travelled, you can always find that from a velocity time graph and working out the area under the VT or velocity time graph. So I've split the area into 3 parts, 1, 2 and 3, and I'm going to work out individual areas of each of these shapes. So we have number 1 is a triangle, number 2 is a square, number 3 is a triangle, and then combine them at the end to find the total distance travelled. So because area 1 is area of a triangle, we've got a half, or 0.5 times the base times the height, gives us an answer of 120 meters. Area 2 is just 25 times 12, because it's base times height, equals 300 meters. And then last, area 3, is the same as the first, we get 36 meters. Combining those all together, our total area is 456 meters. Stopping distance of a car can be affected by the condition of both the tyres and the road. The tread depth of a tyre is the depth of the grooves in the tyre. Most roads have surfaces made of asphalt. Some roads have surfaces made of concrete. Figure 3 shows how these factors affect the stopping distance for a car travelling at a certain speed. So we've got stopping distance on the y-axis, x-axis is the tread depths in millimetres, and we've got 2 lines. One's a dotted line, which represents the concrete roads, and then the black line, which is the asphalt. Give 3 give 3 conclusions about the factors affecting stopping distance that can be made from figure 3. So we've got to look at this graph and try and determine 3 conclusions which are affecting the stopping distance. First thing I notice is that the stopping distances are lower on asphalt than on concrete, and that's for all of the tread depths. If we look at, for example, a point on asphalt here, and we go up to the same point at a certain speed for concrete, this one is 30, stopping distance of 30 for the asphalt, whereas here it's 38. Also can see that as the tread depth increases, the stopping distance decreases. So it has thicker tread, and so therefore is going to have more contact with the roads, and I think that's going to increase its braking ability, which reduces the stopping distance. And then below a certain tread depth, the stopping distance increases much faster. So for asphalt, after about 4 millimeters, so 4 and lower, we see the increase in stopping distance go up, and for concrete, that's below 2.5. You see that sharp, steep increase in the stopping distance. Okay, pause the video. As I move down, these answers will be removed. So because stopping distance is equal to thinking distance plus braking distance, and braking distance can't be below 0, there has to be a limit. And so that's the final question complete.